Piping and piping auxiliaries are an essential part of an industrial facility. Without them, fluids could not be transported from one location to another. One part of an operator's job is to inspect piping systems and report any abnormal conditions that exist. To know what to look for, the operator must have a good general understanding of piping and piping auxiliaries. A rupture disc is one type of device that's used to relieve excess pressure in fluid systems. A rupture disc is designed to rupture or break when fluid pressure exceeds a certain value. When the disc breaks, fluid passes through it and the excess pressure is relieved. This illustration can help explain how a rupture disc works. Under normal operating conditions, fluid flows through the pipe, and the rupture disc blocks the flow through this relief line. If the pressure in the pipe exceeds a certain value, the rupture disc breaks. This allows some of the fluid to flow through the relief line, which relieves system pressure. Now remember, once a rupture disc breaks, it must be replaced before the system can return to normal operation. Here are some examples of typical rupture discs. This one is dome-shaped. The lines on the disc are really small cuts in the metal called scoring. The disc is designed to split at the scoring lines at a certain pressure. This rupture disc is also dome-shaped, but it has a plate with a jagged edge located behind the disc. When the dome begins to buckle in response to excess pressure, the jagged edge cuts into the dome and helps the disc break. A rupture disc usually has a name tag. The name tag gives information such as the disc's burst pressure rating. For example, this disc will break between 19 and 21 psi. Rupture discs are made of different materials for use in different applications. Some discs have a protective coating on one or both sides to protect the disc material from the process fluid. The function of a relief valve is to protect equipment and personnel by relieving excess pressure from a system. Relief valves are connected to process piping and other components. Let's look at an illustration of one type of relief valve. The main parts of this relief valve are the valve body, which has an inlet and an outlet, a disc or plug, a seat, a spring, and a valve stem. During operation, the surface of the disc is exposed to system pressure. When system pressure is within normal limits, the disc rests on the seat and is held in place by the spring, which keeps the valve closed. If pressure in the system exceeds a certain predetermined value, it begins to overcome the spring's resistance and the disc begins to rise off of the seat. When the disc rises, fluid can pass through the valve. This relieves the excess pressure. As pressure decreases, the spring gradually pushes the disc back towards the seat. When the system pressure has decreased to a certain value, the disc is again resting on the seat and fluid no longer passes through the valve. In a relief valve, the amount that the valve opens is determined by the amount of excess pressure. The higher the excess pressure, the more the valve opens. The lower the excess pressure, the less it opens. Relief valves are commonly used to relieve excess pressure in liquid-filled systems. They're not generally used in gas-filled systems because they're not able to release enough gas to reduce pressure quickly. Safety valves are commonly used to relieve excess pressure in gas-filled systems. A safety valve is effective when it's necessary to release a large amount of gas quickly in order to rapidly lower system pressure. This is an illustration of one type of safety valve. Its main parts are the valve body, which has an inlet and an outlet, a disc or plug, a seat, a spring, a valve stem, and a handle, which can be used to operate the valve manually. The disc in this type of safety valve has a lip around its edge. This lip is not exposed to system pressure when the valve is closed, as it is now. When the pressure in the system exceeds a predetermined value, it overcomes the resistance of the spring holding the disc in place, and the disc rises off of the seat. Now the surface of the lip is exposed to system pressure. The increase in exposed surface area allows the disc to be pushed open rapidly. As a result, a large volume of gas passes quickly through the valve and excess pressure is relieved. After the excess pressure has been relieved, the system pressure will begin to drop. When the pressure decreases to a value below the opening pressure, the valve closes quickly. In this topic, we looked at the function and operation of 3 types of protective devices: rupture discs, relief valves, and safety valves. Now check your understanding of these devices by answering a few practice questions. This illustration can help explain how a rupture disc works. Under normal operating conditions, fluid flows through the pipe, and the rupture disc blocks the flow through this relief line. If the pressure in the pipe exceeds a certain value, the rupture disc breaks. This allows some of the fluid to flow through the relief line, which relieves system pressure. The disc in this type of safety valve has a lip around its edge. This lip is not exposed to system pressure when the valve is closed, as it is now. When the pressure in the system exceeds a predetermined value, it overcomes the resistance of the spring holding the disc in place, and the disc rises off of the seat. Now the surface of the lip is exposed to system pressure. Most industrial facilities use steam for heating and other purposes. When steam cools, it condenses into water called condensate, which can cause problems in piping systems. For example, condensate could freeze in piping, which could lead to damage and unwanted shutdowns. Another problem that condensate can cause is called water hammer. Water hammer occurs when an accumulation or slug of condensate is carried along with steam and slams into the wall of a pipe. This is particularly likely to happen at a bend in the piping. Water hammer can cause piping to crack or break. A steam trap is a device designed to remove the condensate while minimizing the loss of steam. Some steam traps also remove non-condensable gases, such as air, from steam systems. Because condensate is heavier than steam, it tends to collect at the low points in a system. For this reason, steam traps are usually installed at the lowest points in a steam system. As an operator, you'll be responsible for inspecting these systems. You'll need to know how steam traps work so that you can tell when they're operating properly and when they're not. Let's take a look at one type of mechanical steam trap. Here's a simplified illustration of a float trap. Let's look inside to see how it works. When condensate forms in the steam system, it drains into the trap. Some steam enters the trap with the condensate. The denser condensate sinks to the bottom of the trap, while the less dense steam stays near the top. A float rides on the surface of the condensate. The float is connected to a valve through a connecting rod. As the level of condensate increases, the float moves upward. This movement causes the valve to open, allowing condensate to flow out of the trap. As long as the level of condensate keeps the float up, condensate will continue to flow out of the trap. As the condensate level decreases, the float drops, causing the valve to close and keeping steam from escaping. Float traps are very effective in removing condensate without losing steam. However, one disadvantage is that air and other non-condensable gases present in the steam system can keep the trap from working properly. If the trap becomes filled with these gases, condensate and steam may not be able to enter. So, float traps are not generally used in systems where air and other non-condensable gases are a problem. In these systems, another type of mechanical trap, called an inverted bucket trap, may be used. An inverted bucket trap is able to handle non-condensable gases. This is an illustration of an inverted bucket trap. Condensate from the steam system slowly enters the trap through the inlet, spills over, and flows into the space between the bucket and the inside casing wall. When the trap is full, condensate flows past an open valve and exits through the outlet. As steam enters the trap and collects in the bucket rises because the steam is not as dense as the condensate. As the bucket rises, the valve closes. Some of the trapped steam flows through a hole at the top of the bucket. However, most of it condenses inside the trap. As the steam condenses, the bucket drops and the valve opens. An inverted bucket trap is able to handle air and other non-condensable gases because these gases are lighter than condensate, and there's not enough of them to raise the bucket. When the trap is full of condensate, these gases rise through the condensate. They pass through the hole in the top of the bucket and exit the trap with the condensate through the open valve. The two traps that we've seen so far, the float trap and the inverted bucket trap, are examples of mechanical steam traps. Like other types of steam traps, a thermostatic steam trap is designed to remove condensate from piping systems that transport steam. The reason for this is to minimize the damage that can be caused by condensate in steam piping. A thermostatic steam trap operates in response to changes in temperature. The difference in temperature between steam and condensate is what causes the trap to open or close. Let's use an illustration to see how one type of thermostatic steam trap works. This trap is called a bellows trap. Its main parts include an inlet, an outlet, a bellows, a valve plug which is attached to the end of the bellows, and a valve seat. Together, the plug and the seat form a valve. When condensate, which is relatively cool, enters the trap, the bellows is contracted and the valve is open. The condensate exits through the trap outlet. When steam, which is relatively hot, enters the trap, the bellows is heated so it expands, closing the valve and preventing steam from escaping. The operation of this type of trap is usually not affected by air and other non-condensable gases because these gases are generally cooler than the steam. The cooler non-condensable gases exit the trap along with the condensate. Part of your job as an operator is to monitor steam traps and make sure they're operating properly. One important thing to check for when you're monitoring a steam trap is leakage out of the trap and associated piping. Typical places where you might find leaks are at piping connections and at points where parts of the trap's body are joined together. Another typical operator check is the trap's temperature. It's important for you to be familiar with the temperatures of steam traps when they're operating normally. Remember that steam piping can be very hot, so you must be extremely careful when you touch any part of a steam system. If a steam trap feels too hot, the trap may have failed open, and steam may be passing directly through the trap. On the other hand, if the trap feels too cool, the trap or its piping may be clogged. If you find a steam trap that isn't working properly, you may be required to take it out of service. But when you do this, be sure to follow plant procedures and notify your supervisor first. Steam trap piping usually includes a bypass around the trap. In order to take the trap out of service, the bypass valve is opened until flow is detected. This allows any condensate in the steam line to drain. There will be some steam loss while this is done. Next, the trap's inlet and outlet isolation valves are closed to isolate the trap from the system. After the trap has been repaired, it can be put back in service. This is done by slowly opening the trap's isolation valves. After the trap's isolation valves are open, the bypass valve can be closed. When the trap is back in service, you should feel the piping near the trap and check the trap's discharge line to verify that the trap is operating properly. If the trap is not operating properly, steam will be blowing by and the trap will be hot. In this topic, we discussed steam traps. We looked at two types of mechanical steam traps and one example of a thermostatic steam trap. We also looked at some typical operator checks that you may be performing. Next, try some practice questions to check what you've learned. Float traps are very effective in removing condensate without losing steam. However, one disadvantage is that air and other non-condensable gases present in the steam system can keep the trap from working properly. If the trap becomes filled with these gases, condensate and steam may not be able to enter. So, float traps are not generally used in systems where air and other non-condensable gases are a problem. In these systems, another type of mechanical trap, called an inverted bucket trap, may be used. An inverted bucket trap is able to handle non-condensable gases. Like other types of steam traps, a thermostatic steam trap is designed to remove condensate from piping systems that transport steam. The reason for this is to minimize the damage that can be caused by condensate in steam piping. A thermostatic steam trap operates in response to changes in temperature. The difference in temperature between steam and condensate is what causes the trap to open or close. Steam trap piping usually includes a bypass around the trap. In order to take the trap out of service, the bypass valve is opened until flow is detected. This allows any condensate in the steam line to drain. There will be some steam loss while this is done. In this part, we're going to follow an operator as he drains a portion of a liquid system so that maintenance can be performed on it. When a liquid system is drained, special precautions may be necessary, depending on the type of liquid being drained. When extremely hot liquids or acids are involved, for example, special procedures and safety gear may be required. So before you begin to prepare a system for maintenance, be sure to check your facility's procedures. The first thing the operator does is isolate the portion of the system to be drained. He does this by closing one or more isolation valves. The operator's next step is to crack open a drain valve to relieve system pressure. When the pressure has been relieved, the drain valve can be opened all the way. When the drain valve is opened, liquid will initially rush through the drain piping. As the system is drained, flow will be greatly reduced. The next step is to open the vent valves. This allows air into the piping, which helps any remaining liquid to drain. Draining is generally considered finished when the flow of liquid through the drain stops. However, flow could also stop if the drain line is plugged, so the drain line should be checked to make sure that it's clear. If there's more than one drain line, check the discharge from all of them. Now, the procedures for draining liquid systems can vary. For example, we just saw a situation where the liquid was allowed to run into a sewer. In many cases, drain lines route liquid to a holding tank or some other containment device. This is especially important if the liquid may be hazardous to the environment. Before a liquid system can be filled, the system must be prepared to keep the liquid from leaking out and to allow for air to be removed as the system is filled. To see how this is done, let's watch an operator fill a system. The operator has been notified that maintenance has been completed and the system is ready to be filled. One of the first things to do is make sure that all the drain valves are closed. Once he's sure that the drain valves are closed, the operator checks to make sure that the vent valves are open. In this system, as soon as the liquid is admitted, air will be purged through the vents. Next, he opens an isolation valve to allow liquid to flow into the system piping. Having the vent valves all the way open helps to purge the system of air and fill it with liquid quickly. However, as soon as liquid starts to come out of the vents, the operator partially closes the vent valves to minimize the amount of liquid that is lost. A steady stream of liquid from the vents indicates that the system is full of liquid. The operator then closes the vent valves. Not all vents are open to the atmosphere. In some systems, vent piping is used to route escaping air and liquid to a containment vessel or a treatment system. When vent piping is used, the operator can determine whether the system is full by touching the vent pipe. If he feels vibration caused by fluid flow, he knows that he can close the vent valve. After the system is full and the vent valves are closed, the system is checked for obvious signs of leakage. If the system is leak-free, it can be put back in service. Well, we've just seen a general procedure for filling a system with liquid. Now would be a good time to check your understanding of the information we've covered. As an operator, you'll probably be responsible for making general checks on fluid systems. In this part, we're going to go over some of these operator checks. We'll begin with one of the most important, checking for leaks. Some obvious signs of leaks include puddles of liquid, wet spots on piping, unusual odors, fine sprays, or puffs of vapor. The entire system should be checked for leaks. This includes devices such as safety valves, relief valves, and rupture discs. Another check is to look for missing or damaged insulation. Cracks, bulges, or tears in the insulating material are signs of damage. If any insulation is missing or damaged, report it so that it can be repaired or replaced. If electrical heat tracing is used in your facility, check the heat tracing controls to make sure that all the required heat tracing systems are operating properly. If steam heat tracing is used, check the steam pressure to make sure that steam is available. Then make sure that the steam flow control valve and the steam traps are functioning properly. The general operating checks we've just covered apply to most fluid systems. Your facility's specific procedures will have more details. In this topic, we watched an operator go through typical procedures for draining and filling a liquid system. We also went over some of the most common operator checks on fluid systems. Now try a few practice questions to check your understanding of this material. The first thing the operator does is isolate the portion of the system to be drained. He does this by closing one or more isolation valves. The operator's next step is to crack open a drain valve to relieve system pressure. When the pressure has been relieved, the drain valve can be opened all the way. The operator has been notified that maintenance has been completed and the system is ready to be filled. One of the first things to do is make sure that all the drain valves are closed. If steam heat tracing is used, check the steam pressure to make sure that steam is available. Then make sure that the steam flow control valve and the steam traps are functioning properly. This operator is in the process of draining a portion of a liquid system. He has just relieved system pressure by cracking open the drain valve. This operator is draining a portion of a liquid system. He has just opened the drain valve. What's his next step?